Here we study Jacobian matrix. So topic of this lecture is following. The topic is Jacobian matrix. Matrix of function f equal to f1 and so on. Fm. So m many components are there. So this is from Rn to naturally Rm. So basically we find Jacobian matrix of this function f from Rn to Rm in terms of its component functions. So here is the theorem number 1. So statement is the following: if f equal to f1 and so on, if m from Rn to Rm is differentiable at A belongs to the domain of f, that is Rn. So if this function is differentiable at A belongs to Rn, then the partial derivatives of the component functions, then this is partial derivative of ith component function with respect to the jth variable at the point A for I lies between 1 and m, and j lies between 1 and n exist. And so this is the first statement. Moreover, so furthermore, the Jacobian matrix f prime at the point A, this is given by the jth partial derivative of ith component function at the point A, and this is m cross n matrix. So this is m cross n matrix. So recall that this is basically the matrix of the derivative. So df, the derivative of f at the point A, this is basically the linear transformation from Rn to Rm, and the matrix of this linear transformation with respect to the ordered, so the standard ordered basis, standard ordered basis of the Euclidean spaces Rn and Rm. So the matrix of the derivative df at the point A from Rn to Rm, this is a linear transformation with respect to the standard order basis of Rn and Rm, that is called Jacobian matrix, and this is the Jacobian matrix of this derivative of f at the point A. And the Jacobian matrix is given by this expression. So well, now we prove this theorem, proof of theorem 1. So first we prove the theorem. So for the special case m equal to 1, so consider, suppose m equal to 1, so that the function f is from, so consider m equal to 1, so that the function f is from Rn to R, so real valued. So to show that, to show the jf, so partial jth partial derivative of f at a exists. So exist for j equal to 1 to n, exist for j equal to 1, and so on up to n, and the Jacobian of f, Jacobian matrix of f at the point a, this is equal to dj f at the point a, this is 1 cross n matrix. So this is what we need to show. Well, to prove, so we define a function h from R to Rn. So define, so well, before defining, let us consider a equal to the n tuple a1 and so on an. This is in Rn. So now we define h, so from R to Rn by h of x. This is equal to a1 and so on h sub j minus 1, and so sorry, this is basically not h, this is a sub j minus 1, and the jth component is x, then a j plus 1 and so on. The last component is an. Well, then we have the following: h at the point aj, this is equal to a. Second, h is differentiable on R, and h prime at a j, this is equal to, so this is the Jacobian matrix of h at the point aj, and that is the matrix of order n cross 1, and the matrix is given by 0 and so on. Here we have 1, then so this is the jth entry. So at jth position we have 1, and all the other position we have 0. So this is the derivative of h. So now consider, well, so we have, so let me draw a picture. So this is R, here we have Rn, and so from R to Rn we have h, and from Rn to R, here we have f. The composition function, this is f composed with h, and so by definition, so we have the jth partial derivative of f. So the jth partial derivative of f at the point a, this is equal to basically the derivative, the ordinary derivative of, so dx, ordinary derivative of f composed with h at the point a j, and this is equal to, by applying chain rule, we have f prime at the point h of a j times h prime at the point a j. So here, so from from here. So h of aj, that is equal to a. So that is, so a prime, this is a times h prime at aj, that is equal to the column vector with entries at jth position 1 and rest are 0. So this is 0. So what is this? This is basically the jth entry. So this is basically the jth entry equal to the jth entry of 1 cross n matrix f prime a, and therefore this implies f prime of a, this is equal to, so the first component is, so jth component is this, so the first component is d1 f a, second component is d2 f a, and so on. The last component is dn f a, so the nth partial derivative of f at a. So this proves the theorem 1 in the case when m equal to 1. Now we consider the general case. Consider the general case m greater than or equal to 1. Actually, this general case follows from the theorem. So let us recall the theorem. So we have proved earlier. So it says that if f equal to f1 and so on, f m from Rn to Rm is, so this is a function, and so let this is a function and a belongs to the domain of f, that is Rn, then f is differentiable at the point a if and only if its component functions are differentiable at the point a. So f is differentiable at a if and only if it is if and only if its component functions, if and only if I is where I equal to 1 and so on. So many component functions are there. So if and only if i's are differentiable at a, and moreover the derivative of f at a is given by following: derivative of f1 at a and so on, derivative of fm at a. So this theorem, so this theorem we have proved in lecture 4. So reference lecture 4 part 2, and this is probably theorem 3. So therefore, thus f prime of a, the Jacobian matrix of a is the m cross n matrix whose with ith row is f, So with ith row is fi prime at a, and so this completes the proof of theorem 1. So now we have the following natural question. So what about the converse of of theorem 1? So let us see what is the converse first. So converse is following. So suppose so this is the converse. Suppose f is a function, f equal to f1 and so on, f m. This is a function from Rn to Rm, so Rn to Rm, and a belongs to Rn, such that all the partial derivatives di f j at a exist for I lies between 1. So for I lies between 1 and n, that is the number of variables, and j. So okay, let me change the notation. So this is ith component function, jth variable. So I lies between 1 and m, j lies between 1 and n. Okay, so the converse is following. Suppose f is a function from Rn to Rm and a belongs to Rm, with all the partial derivatives of component functions exist. So does it imply that f is differentiable at a? So basically here in theorem 1, in theorem 1 we have shown that if f is differentiable, then all the partial derivatives of the component functions at that point exist, and so the converse is, suppose the partial derivatives of the component functions exist. So then does it imply that f is differentiable at a or not? And answer of this question is no. So for an evidence, we have the following counter example. So consider f x comma y. This is equal to x times y over x square plus y square, where x comma y, this is not equal to 0 comma 0, and for x comma y equal to 0 comma 0, the functional value is 0. So f of xy equal to 0 when x comma y this is equal to 0 comma 0. So this is the function. Then the partial derivative of f with respect to the first variable x. So the partial derivative of f with respect to the first variable x is at the point 0 comma 0. This is equal to 0, and which is equal to d2f 0 comma 0. So partial derivative of f So partial derivatives of f, all the partial derivatives of f at 0, 0 exist, but this function f, so but f is not differentiable at 0, 0, not differentiable at 0, 0. So notice that this function is not continuous, is at 0, 0. So that's why, so not, f is not continuous at 0, 0, and this implies f is not differentiable at 0, 0. So you know that if a function is differentiable at a point, then the function is continuous at that point. Okay, so now we have a remark. So we have a remark here. So although this converse is not true, so under some, so with some additional condition, this converse is also true. So we remark here that converse is true if an extra hypothesis is added. So with this extra hypothesis, we have the theorem 2. So theorem 2 says that theorem 2. So it says that, so this is the statement, let f equal to, again, f1 and so on, fm. So these are the component functions from Rn to Rm. So this is the given function, and A belongs to the domain Rn. Then the derivative of f at the point A exists. So this exists if first of all the partial derivatives, so derivative of ith component function with jth variable for I lies between 1 and m, so m many component functions are there, and j lies between 1 and number of variables, that is n. So the derivative of f at the point A exists if all the partial derivatives of the component functions exist in some open neighborhood of A and are continuous at the point A. So this is the additional condition. So if the partial derivatives of the component functions, these are continuous at A, then f is differentiable at the point A. So again, so In the proof of theorem 2, we consider the basic case, that is m equal to 1. Consider m equal to 1. For m greater than or equal to 1, the general case follows from this theorem. Okay, so here also we prove this theorem for the case when m equal to 1. So consider m equal to 1, so that the function f is from Rn to R. So real valued multivariable function. Now let h equal to h1 and so on hn, and a equal to a1 and so on an. This belongs to Rn. Then, so basically we have to show that derivative of f at a exists. So we start with f a plus h, so by definition, so minus f of a, and this is equal to f of, so this is equal to, so f of a1 plus h1 comma and so on a n plus hn minus f of a, means the n tuple a1 and so on an. So we write this quantity as follows: f of a1 plus h1 comma a2 and so on an minus f of a1 and so on an, then plus f of, so first let me write the minus. So we have added this term. So here we take minus of f a1 plus h1, then comma a2 comma a2 comma and so on an, and here we take a1 plus h1 comma a2 plus h2, then a3 and so on, last component an. So in this way we write the last term is f. So this is a plus h, that means a1 plus h1 and so on an plus hn, minus f, so minus f of a1 plus h1 comma and so on a n minus 1 plus h n minus 1 comma an. So now consider, so this is equal to this term, so let me erase this, plus this term and so on plus this. So let us consider this summand. Now if a1 plus h1 a2 and so on an minus f of a1 and so on an. So let us compute this quantity. So here we apply mean value theorem. So let's first define G from R to R. So define by G of T, this is equal to F, first component is T, and the rest of the components are A2 and so on, AN. So G is differentiable. G is differentiable real valued function on R. So we have, so this is equal to G of A1 plus H1 minus G of A1, and apply a mean value theorem on G to get the following H1. So difference between these two. So this is H1. So let me put absolute value. Absolute value of H1. So this, otherwise this is minus H1. So times mod of G prime some point B1, where I'll explain what is B1, and this is equal to mod H1. So G prime of B1, that is actually the first partial derivative of F at the point, so C1, where C1 equal to, so here let me describe what is B1. So B1 is is a point that is real number in the interval with endpoints at A1 and A1 plus H1. Okay, and C1 equal to G of B1, that is equal to B1 comma A2 and so on AN. And note that if H tends to 0, say if H1 tends to 0, then C1 tends to the point A. So similarly for J lies between 1 and N, we have a generic term in the, so A1 plus H1 comma and so on, comma AJ plus HJ, so AJ plus HJ comma AJ plus 1 and so on AN, minus F of A1 plus H1 and so on AJ minus 1 plus H sub J minus 1 comma AJ comma and so on AN. So absolute value of this is equal to H, absolute value of Hj times the jth partial derivative of, like here, so here we have the jth partial derivative of F at some point Cj, where Cj equal to, like here, so we have A1 and so on, A j minus 1, comma Bj, comma A j plus 1 and so on, An and Bj is a point in the interval. Bj is a point in the interval, open interval with endpoints at a j and a j plus hj. Therefore, we have absolute value of a f a plus h minus f of a minus summation dj if at the point a times hj. So over summation over j equal to 1 to n. So well, this is lesser or equal to 1 over, so here we have 1 over norm of h. So this is lesser or equal to 1 over norm of h times hj mod of hj times dj f cj dj f of cj minus dj f at a, and so this is summation over j equal to 1 to n, and this is less or equal to for every j. So let us write 1 over hj inside the summation. So this is over norm of h. So now absolute value of hj over norm of h, that is always less or equal to 1. So this quantity is less or equal to summation j equal to 1 to n mod of dj f at cj minus dj f at a. So absolute value of this. Now we have h tends to 0 implies cj tends to a, and continuity of the partial derivative, jth partial derivative of f for every j lies between 1 and n. We have cj minus d f at a, so dj, so at f this quantity tends to 0 as h tends to 0. Therefore we have, so this finite sum tends to 0 as h tends to 0. So this implies limit absolute value of f a plus h minus f of a minus summation dj f at a times h j absolute value over norm of h. So this limit as h tends to 0, this is equal to 0, and this implies by definition df, the derivative of f at the point a is given by, so this is a linear transformation from R into, so from R into R, so this is equal to summation d j f at a hj summation over j equal to 1 to n. Okay, so that is f is differentiable at a and its derivative is given by this equation. So this completes the proof of theorem 2. So well, now we have one more theorem, theorem 3. Well, so here let g1 comma g and so on gm, these are functions from Rn and values are in reals. So R into R, so be continuously this be continuously differentiable at A. That means these functions are differentiable, and so all the partial derivatives, so that implies partial derivatives of the functions gi's so exist, and this is continuously differentiable means its partial derivatives are continuous. Okay, so at the point A, and let f is a function from R m to R. So this is a real valued, and let this be differentiable at, so A belongs to here Rn, and so f is differentiable at g1 comma acting on A comma and so on gm acting on A. So g1 of A, this is real, so these are real, so this is m tuples of, so m tuple of reals, so this belongs to Rn, and f is differentiable at this point g1 of A and so on gm of f, that is that belongs to Rm. Now we define now the function capital F, that is from Rn to R. This is defined by, now define f by f of x, this is equal to small f composed with, so small f of g1 of x comma and so on g m of x. So well, so let me write the conclusion, then I'll explain this function. So then now the ith partial derivative of f at the point A is given by the following expression dj f at the point, so jth partial derivative of f at the point g1 of A and so on gm of A times d di, so ith partial derivative of the jth function gj at A. Summation is over j equal to, so summation is over j equal to 1 to m. Well, this is the theorem. Now, okay, let me explain the function. So let g equal to G1 and so on, Gm. Suppose this is a function from Rn to Rm. Then so what we have is from, so let me draw a picture here. So here we have Rn to Rm. This function is G defined here, and from Rm to R we have the following function, small f. So small f, this is function from Rm to R. So here we have the composite function f composed with G, and this is basically capital F. Now we compute the ith partial derivative of the component. So the function f. So we have f of x equal to f composed with g of x, and g is differentiable at the point. So these are continuously differentiable at a, so g is also differentiable at a, so because component functions of g are differentiable. So g is differentiable at a, and f is differentiable at this point. So by hypothesis, f is differentiable at, let's say this is equal to, let's say b. So we have not used b, so this is b at b. Therefore, by chain rule, applying chain rule, we have capital F prime of A. So this is equal to F prime G of A times G prime of A, and F prime of GA, that is equal to D1. So D1, so recall that F is from function from R M to R. So F prime of some point F prime of, let's say, so this is B. So this is equal to D1 F. So for first partial derivative of F at point B, and so on, dm F at point B. So here we have F prime of GA. So GA is equal to B, we have considered. So we have F prime of GA equal to this, dm F at B, and G is function from Rn to Rm, and so this is function from Rn. So G prime of A, this is a matrix of order m cross n. Okay, so times G prime of A. And on the left hand side we have F prime of A. So and F prime of, so F is from Rn to R. So the so the Jacobian matrix of F at capital F at A. So the left hand side here is D1 F at A, and so on, D of N F at A. So this is N cross 1 cross N matrix. So 1 cross N matrix. And now the jth column of G prime of A is given by following. Jth column G prime of A is how D J G G1 at the point A. Second entry is D J G2 at A, and so on. D J G M at A. So this is the jth column of G prime of A. Now so what we have to prove, so ith component, so ith component of F prime, so di of F at A, so this is equal to this row matrix multiplied with ith column. So instead of jth column, we need ith column of G prime of A. So this is ith column of G prime of A, that is equal to D I G1A, D I G2A, D I GM of A, and this is equal to, so ith component of this is equal to a multiplication of this row with the ith column of G prime of A, and that is equal to, so D1 F at B times D I G1 of A plus, and so on. The last term is dm F at B times di of gm at A. And in short, one can write this is equal to summation of dj F at, so at the point, so this is actually B, this is B at the point B, then di gj at the point A over summation over j equal to 1 to m. And recall that B equal to G1 of A, comma, and so on, G M of A. And this is what we wanted to prove. So this completes the proof of theorem 3. So stop here.